Last day we had a pretty heavy class. We discussed anthracene and not naphthalene, sorry, naphthalene. You can work out anthracene by yourself. It's doable. It's just one more ring and it's symmetric. Naphthalene, right. And we did it in a good amount of detail. So today we are going to discuss transition metal complexes as you see on the projection. But we are not really going to work out everything. By now you know very well how to construct the reducible representations, how to break them down, how to generate SALCs using projection operators. So there is no point in going through every step anymore. But my request to you is that after you go back from the class, please work out every step by yourself. Okay? Just watching a cricket match, you might think it is very easy. But when you try to play yourself, that might be quite a different ball game. So please don't give up the habit of working out these examples. And my suggestion is work out as many solved examples at least from Cotton's book as possible. Not only here, but also in organic chemistry. This year we are not discussing the pericyclic reactions. We did it last year, but then I think that is one thing that we could do without. We have done many other topics that we did not discuss last year. So pericyclic reactions is out of syllabus this year. But for organic molecules as well as inorganic complexes, please work them out, as many of them as possible, by yourself. Okay? Right. Now, everybody has studied about transition metal complexes at different stages. And you know that there are different kinds of theories, right, to describe these complexes. Who discovered transition metal complexes? Werner, right? That rosio-cobaltic chloride, prazio-cobaltic chloride and so on and so forth. So that was a long time ago. I think it was about 120 years ago that transition metal complexes were first prepared. And then to understand what is going on there, several theories have been proposed. The simplest theory, as everybody knows, is about dative bonds or coordinate bonds. That is why they are called coordination complexes in the first place. But there are other theories like crystal field theory, ligand field theory and molecular orbital theory that work equally well by and large to describe the transition metal complexes. We are not going to discuss valence bond theory. Even valence bond theory can be used to some extent. We won't have time for ligand field theory, but today what we will do is we will discuss crystal field theory a little bit and then see whether we can go on to molecular orbital theory. We will restrict ourselves to the octahedral complex today, and I will ask you to work out tetrahedral complexes by yourself. Next day, let us see what we do, because we have two things to discuss. One is hybrid orbitals, the other is molecules like complexes like ferrocene. Okay? Let us see what we do next day. I have not made up my mind yet. But the point is, no matter whether you are talking about crystal field theory or ligand field theory or molecular orbital theory, I believe everybody understands that the discussion is centered mainly on d orbitals of the transition metal ions, right. The reason why you get such unique compounds of transition metal ions is the d orbitals. So this entire topic is really about d orbitals. So maybe you know what we are going to say next, but it does not harm, since d orbitals are so important for us in this discussion, to revisit d orbitals and understand d orbitals thoroughly before we proceed to the metal complexes themselves. I am grateful to Professor Shashidhar. He has been careful to put in his name in the slide also. For the next few slides, these are I think 15-year-old slides. He did a fantastic job of making a presentation on shapes of orbital, hydrogen atom in general. Apparently he has more, but this is something that I have used I do not know how many times. They are really nice slides. So I am proud to lift them from Professor Shashidhar, Skitty. Okay. So these are the d orbitals, right? Everybody knows the names in any case. So 3d x square minus y square. So 3d x square minus y square is given by 1 by 81 root over 2 pi z by a to the power 3 by 2, z by a square r square e to the power minus zr by 3a sin square theta cos 2 phi. Please, please, please do not memorize this. I got to know later that last year a student of mine memorized some character tables. Kindly do not do such things. I get extremely scared when I hear this. Do not remember the form of dx square minus y square orbital. But what we want to learn today is that why is it that the dx square minus y square orbital is called the dx square minus y square orbital. So I think in this expression for the x square minus y square, dx square minus y square orbital, you can make out which is the radial part and which is the angular part, right? Which is the radial part? R square e to the power minus zr by 3a. So it is no surprise that this is what the radial part looks like. R square increases with increase in r and e to the power minus zr by 3a decreases in r. So the product of course goes through a maximum. And you can work out where that maximum is. I will not go into that. Okay. Let us focus on the angular part. Can anybody translate this angular part for me? Sin square theta cos 2 phi. I want it translated to Cartesian coordinates. Can you do that? So what is cos 2 phi? So if we have not forgotten the relationship between r theta phi and xyz, I will tell you the most difficult one, z equal to r cos theta. Now you tell me what is x equal to? R sin theta cos phi. And what is y equal to? So by using that, can you translate this sin square theta cos 2 phi into something in x and y and z? It is not necessary that x, y, z everything will be there. R square will get cancelled with the r square that is there. Right? So x square minus y square. So where do the nodes appear? Okay, well, those who are still working, believe us, it is x square minus y square. You can work it out later. Otherwise, you will miss out on the next discussion. Where do the nodes appear? Right. What kind of nodes are they? Radial nodes or angular nodes? Angular nodes, right? You are equating the angular part to 0. Nodes you get there from are angular nodes. So x square minus y square equal to 0 or x square equal to y square or x equal to plus minus y, right? That is the equation of the angular nodes. Now x equal to plus minus y represents what kind of a surface? In 3 dimensions? Planes. X equal to plus minus y. If you are working in the xy plane, then there are 2 lines. If you are working in xyz space, then there are planes. Where are the planes? Here are the planes. These 2 lines are sections of the planes, right? The planes are like this. Okay. So that is why 3d x square minus y square, or rather dx square minus y square orbital is called the dx square minus y square orbital, because there is an expression of x square minus y square. There is a term of x square minus y square in the expression of the orbital, and when that is equated to 0, x square minus y square equal to 0 is the equation of the nodes. Okay. So this is why it is called x square minus y square. What is a node? A node is a point or line or plane, whatever, with respect to which the wave function changes sign. Please remember, wave function has to change sign. Okay. Wave function would become 0 at infinity also, e to the power minus 0 by a0. At r equal to infinity, the wave function would become 0. But r equal to infinity is not a node, because wave function becomes 0, it does not change sign. At a node, the wave function has to change sign. Alright. So if these are nodes, then what will happen? You start with plus, you go across the node, you should get a minus lobe, then go across, you get plus again, go across, you get a minus, and just to check, if you go across this plane now, you go from minus to plus. What is this plus and minus? Electron is negatively charged when it is here, electron is positively charged when it is here. No? Then what? Phase of what? Phase of what? Wave function, right. Phase of the wave function, whether the wave function is positive or negative. Alright, got it? Right? So you understand what it is. Now I want to make a point. If I want to talk about symmetry transformation of this dx square minus y square orbital, will you agree with me that it is enough for me to consider the transformation of these planes? I will forget about what the orbital looks like. As planes are, the cross section of the plane is a straight line. It is easier for me to deal with. I will work with the transformation of the planes. Will that not mirror, or rather will that not map the transformation of the orbital itself? Example, let us say there is a C4 axis perpendicular, okay. C4 is not good. C4 is not good. Let us say there is a C8 axis. C8 means how many degrees? 345 degrees. Then? So you have to speak up. I am a little deaf. I cannot hear if you whisper. 45 degrees. So I turn it by 45 degrees. Where will this line go? It will become the y-axis. Where will this line go? It will become the x-axis. What will happen to the lobes? They will also turn. But this lobe will still be between this line and that line, isn't it? So what I am saying is, instead of working with the lobes, I might as well work with the planes. There is no difference. Achal, do you agree with me? If you don't, please express yourself. Make sense? Because when you move the planes, the lobes are defined with respect to the planes, isn't it? So they will also transform accordingly. Orko. No, I just took a C4 axis. Whether we have a C4 symmetry or not depends on what point group it is. I just used an arbitrary example. Huh? Okay. Yes. That is right, but that does not matter. The lobes will still transform that way, isn't it? Whether it is a symmetry operation or not, that comes later. All I am saying is that transformation of the planes is going to define the transformation of the lobes also. Okay, that makes sense? Yes.
What do you mean by phase? When we are saying the phase is positive and the phase is negative?
Do you remember what the 1s wave function looks like? This is lecture 22, slide 1. 1s wave function, what does it look like? Help him. So what will the radial part look like? Of course, 1s is all radial part, isn't it? So if I plot it like this, it's an exponential decay, isn't it? 1s. So is the wave function negative anywhere? No, it's positive everywhere, right? So that is the phase of the wave function. What about 2s? You remember what 2s looks like? If you start with positive, it goes, there is a node, right? And then it's like this. So this is plus phase, this is minus phase. The sign of the wave function.
Sign of the wave function is phase.
And that is relative. I might as well write this as negative, this as positive.
The wave that we say phase difference in the waves.
So if this is a wave, this is positive phase, this is negative phase.
Yeah.
So this is also kind of a wave, right? It's a wave function. It's the same thing, plus or minus.
But in general, when we talk about waves, so we talk about sine waves. So we talk about the theta that is there and theta plus phi.
That is right, but whatever you do, it is plus here and minus here. It's just a sign, isn't it? So the sine theta varies from say plus 1 to minus 1. As long as it is between 0 and 0, 1 and 0, phase is positive. When it is from 0, minus 1, 0, phase is negative. Same thing. This is the sign. Mehak, question. Forgot?
Basically, so when you said that the mirroring of the plane is same as the mirror, like
No, no. Transformation of the plane, what should I say, is the same as the transformation of the orbitals. That's what I am saying. Fine. So, you understood 3D x square minus y square? Okay. Next one is xy. Okay, xy and yz and zx are more or less similar. We will discuss only one. If you look at xy now, what is the angular part? Sin square theta, sin 2 phi. So, what is sin 2 phi? So, will you agree with me that that is xy divided by r square? Huh? So, where are the angular nodes? Xy equal to 0. Xy equal to 0 means x equal to 0, y equal to 0. What is x equal to 0? No, no, no. 3D. YZ plane. And what is y equal to 0? XZ plane. So, YZ and ZX planes are the nodal planes here. And then again you go plus minus, minus plus, plus minus, minus plus as you cross the nodes. Okay. So, that is why this dxy orbital is called dxy orbital. Got it? I might as well write xy by r square here. Understand? So, the orbital also will transform in the same way as xy will transform. So, that is another way of thinking. You can think that the orbital will transform in the same way as the nodal planes will transform, or you can say that the orbitals will transform in the same way as xy will transform, because you have xy there, right, in the expression of the orbital, right, isn't it? Everything else is totally symmetric. What I am saying is, one way of thinking is that you transform the planes, okay, and the orbital will follow. That is one way of thinking. The other way of thinking, perhaps a simpler way of thinking, is that just look at the expression of the orbital. The expression itself contains xy, right, and everything else is totally symmetric, right. So, the orbital will transform in the same way as xy transforms. So, whichever symmetry species xy belong to will be the symmetry species of this dxy orbital. That is perhaps a little easier to think rather than thinking of how planes transform. Fine. This is the orbital I like most, 3D z square, and 3D z square, you see, it has 3 cos square theta minus 1. Everybody knows that cos square theta would be z square by r square. So, 3 z square by r square minus 1. Since you have z square there, you call it 3D z square, right, simple. Now, there is something more to it, we will come back to that, but before that, where will the angular node be? Z equal to plus minus r. Now, z equal to plus minus r, that 3 is also there. 3z square equal to r square, right. So, that 1 by root 3 factor will come. Okay. Now, the point is, this is a little different from the earlier one, because r is also there, isn't it. So, when we draw a section, we just draw 2 lines, okay. But if you think actually in 3D, you are familiar with this kind of a picture, 3D z square, where is the, what is the shape of the node? Is it really 2 planes? No. What is it? It is like 2 funnels, isn't it? So, this is the nodal surface, actually it is only one surface, not 2, or you can say this is one and that is one, right, fine. Now let us come back to 3D z square from a different angle. I told you that the name is 3D z square, isn't it, right? But in India, in other countries also, we often have more than one names, right. One is the proper name, the official name, the other is nickname, isn't it, right. So, Elizabeth is Beth or Liz. Now, I know you are not expecting that example, but right. So, that kind of thing. So, The issue is this 3dz square is actually only a nickname. It is not really a full name. Okay? It's only a nickname. Why do I say it's only a nickname? Because don't forget that this r is actually a spherical polar coordinate, isn't it? It's not Cartesian coordinate. Can you represent r in terms of Cartesian coordinates? What is it? What is r square? X square, r square. R square there is no root. R square is x square plus y square plus z square. So if I write that, then what does it become? 3z square divided by x square plus y square plus z square minus 1 equal to 0. Right? Now simplify that expression and tell me what do you get in the LHS. What is it? 2z square minus x square minus y square equal to 0, isn't it? So I represent it completely in Cartesian coordinates, then the full label should be 3D 2z square minus x square minus y square. Alright. And I have no option but to use this because z square does not even appear in the character table of octahedral point group. What appears is 2z square minus x square minus y square. So I have no option in this case but to use the full label. The full label is 2z square minus x square minus y square. Alright, understood? Okay. Now I want to know where they belong in the character table for OH because we are going to talk about octahedral point group today. As we have discussed earlier, when you have a bare metal atom, bare metal ion, what is the point group of bare metal ion? What shape is a bare metal ion? It is a sphere, the perfect shape, right? How many C2 axes are there? And how many C298 axes are there? Infinite, right? So it has infinite number of axes of different kinds, it has infinite number of planes of different kinds, and it has one number of point of inversion. Don't think it has infinite points of inversion, it doesn't, there is only one. Okay, so that is called the R3 group, the spherical group. Now in that R3 group, what happens is all the d orbitals are degenerate. All the d orbitals belong to the same group and they are degenerate. Not so in OH point group. So in OH point group you see you have A1G, A2G, EG, T1G, T2G, A1U, A2U, EU, T1U, T2U. What is the highest dimensionality of any symmetry species? 3. There is no 5-dimensional symmetry species. So isn't it obvious that in an octahedral complex where point group is OH, it is impossible that all the 5 d orbitals would have the same energy, isn't it? They have to belong to different symmetry species. Okay? Which symmetry species? That can come directly if you look at the character table. What are we looking for? We are looking for 2z square minus x square minus y square. We are looking for x square minus y square. We are looking for x, y, y, z, zx. And see, they are there in the character table. This 2z square minus x square minus y square and x square minus y square belong to EG point group, doubly degenerate. And x, y, y, z, zx belong to T2G point group. What am I saying? T2G symmetry species, EG symmetry species and T2G symmetry species, right? That is why they have to have different energies. UG nahi, you are UG, this is EG. EG, T2G, alright. So this is why in an octahedral field you expect the d orbitals to split into two groups. One group of 2, EG group, the other group of 3, the T2G group. Where does the name EG come from? Where does the name T2G come from? Mulliken nomenclature of the symmetry species to which the respective d orbitals belong. So now after all these years of studying chemistry, the origin of the name is known to you, all right? Fine. Okay. Now, this is not something I am going to discuss because you have studied this many times. You tell me which one is destabilized to a greater extent in an octahedral field. You remember crystal field theory, isn't it? Remember crystal field theory? All orbitals are actually destabilized, isn't it? That is the consideration of crystal field theory. It is just that some are destabilized to a greater extent. That is what gives rise to a relative stabilization of one of the groups, relative destabilization of the other group. Okay. So, which one is destabilized to a greater extent, Eg or T2G? Why? They are along the axis, and the approach of the ligands is also along the axis. Okay. And so that is one question. Second question I have is, what is a high spin complex, what is a low spin complex? You better tell me. So right now we will go with the simplistic view that inorganic chemists are comfortable with and just say unpaired electron, no problem. Okay. So more unpaired electron is high spin and less unpaired electron is low spin. Okay. Which configurations yield high spin complexes, which configurations yield low spin complexes? What are the configurations we are talking about? D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Is it possible for you to get a high spin complex and a low spin complex for D1? No, right? What about D2? Can you get high spin complex, low spin complex? No. Why not? Because they will be in the lower level. So what we are saying is this. Okay. This is what an octahedral complex would look like. You have a central metal ion, okay, and you have these ligands approaching along the axis because it is octahedral. Okay. Now see, there are two kinds of d orbitals, right? One is like this. Which d orbital is this if these are x and y axis? So now dx square minus y, you see ligand approach is directly onto x square minus y. Now if I draw it like this, once again x and y, this is another kind of d orbital. What is it? xy, right? For xy, the approach of the ligands is not head on, right? So this repulsion that you have here is less than what you have here. Understand? That is all we are saying. So which point group is, which symmetry species is this? Eg, right? This belongs to Eg symmetry species. It has Eg symmetry. And this is T2G. There are three: x, y, y, z, zx. And this you have z square and x square minus y square. All right? D1, D2? Oh, I see. Fine. No, so you understand why Eg is destabilized and T2G is stabilized. Eg is destabilized, right, with respect to T2G? So Eg is doubly degenerate, T2G is triply degenerate. So these are all same energy. I am just drawing them apart for the sake of convenience. So what I am saying is, for D1 configuration, you have one electron here, right? And it can only be either here or here or here, isn't it? So spin is only, what is the spin? Plus half. Okay. If it is D2 configuration, where will the second electron go? One here and one here. Is there any other possibility? D3, third electron will go here, right? Now D4, when we go to D4, there are two possibilities. 1, 2, 3, 4. This is one possibility. The other possibility is 1, 2, 3, 4. Okay. How many unpaired spins do I have here? 4. How many unpaired spins do I have here? 2. So, this is a high spin complex and this is a low spin complex. Alright. When will high spin complexes form? When will low spin complexes form? It depends on the ligand, but then a little further. Exactly. So, energy gap between T2G and EG. If the energy gap is very large, then the electron will rather pair up and stay here. If the energy gap is not very large, then the electron wants to stay by itself. Understood now what is high spin, what is low spin complex? Okay. And we have already discussed which configurations yield high spin complexes and which configurations yield low spin complexes. So, you can look up any inorganic chemistry book if you require, everything is discussed there.